Okay, yeah, thank you for the introduction. And this is a great pleasure to present my work in this CECS seminar series. And today we'll talk about my efforts to promote human-robot symbiosis with the intelligent robot and neural interface for personalized assistance. A brief background about myself. So I joined the UCF in August and new faculty here in the Department of Mechanical Engineering. And I'm also a member of Disability, Aging, and Technology Cluster. And I got my bachelor degree in automation and a master degree in control theory and engineering in China. And then I attended my PhD degree in biomedical engineering from UNC Chapel Hill and NC State University. After that, I got extensive training in the rehabilitation and neural interface at Shirley Ryan Ability Lab at Northwestern University. So my research interest includes personalization of wearable robots, neural-machine interface, artificial intelligence for human-robot system, and gait rehabilitation, as well as human-robot interaction. Along with my research, I would like to teach courses related with robotics, neural-machine interface, and control, and human biomechanics. And I will start so my overall goal is to achieve those human-robot symbiosis to provide personalized and coordinated assistance for the wearable robots. So here for a human-robot system, like human wearing a prosthetic device or human wearing exoskeletons, it is typical that we use a hierarchical controller to mimic like a human locomotion, for example, walking level ground, upstairs, downstairs, or ramps. So to achieve this human-robot symbiosis, it's critical that the robot provides right amount of assist at the right time, which means that we need a personalized assistance to match the humans or the user's physical condition, and also we need like a neural interface to understand what the human want to do. This will lead to my two research topics. One is on the personalization of lower limb robotic knee prosthesis. Another one on the high-density EMG-based neural machine interface. I want to give a brief background about the power knee prosthesis. As you can see here, compared to passive prosthesis, the power knee prosthesis can restore like natural gait in different terrains. For example, like this is upstairs, ramp, and level ground. On the right side, we can see this is a typical procedure for personalized prosthetic device. Here, the clinicians will change the parameter, change the configuration, and make observation. This configuration procedure is, we can see, is time-consuming, costly, and kind of subjective, and also kind of inefficient. Imagine that we need to configure those parameters for all those terrains. It will be like a daunting task, right? So the question is, how can we facilitate clinicians to effectively and efficiently configure the power prosthetic device? This will a bit more information about the prosthesis control. Here is a typical finite state machine impedance controller for power knee prosthesis. So typically, the gait cycle is divided into stance flexion, stance extension, swing flexion, and swing extension. In each phase, we use the impedance controller to mimic the biological knee function, as here. So now comes to question, how can we configure these 12 control parameters so that the knee profile, the robotic knee profile, matches the target or biological knee profile, as here, like the red is the target. And so we simplify this problem as like peak error and duration error for each phase. And so this is challenging because like there is propagation, like the error will propagate throughout the gate cycles. Like one error could trigger the others, right? So that is the and also these high dimension parameters. Now come to our proposed solution. And the left side is a typical human robot system with a finite state machine impedance controller. On the right side is our proposed ADP controller, which include 4 ADP blocks, one for each phase. And here I will skip the details, the technical details. The main point is we use this parallel structure corresponding to the gate phases to personalize the prosthetic device with the human in the loop. As we are the first group working on this, it will be like we want to test the feasibility of the algorithm. Here we test it with a simulation study. So basically, we validated the algorithm with a simulation study. Here with the human prosthesis model in the loop. And after the tuning or configuration, the knee kinematics or knee profile approach the target, as you can see here. And also the root mean square error decreased significantly after the configuration. And then we move forward to with the human participants. This is here we have the ADP framework with human in the loop. And the ADP is able to find the optimal parameters to approaching the normative knee kinematics. As here you can see the mean square decrease after the tuning. Here the naive ADP means that the controller initialized is randomly initialized without prior knowledge. And the right side is the result from an experienced ADP. And you can see that the angle error and duration error both decrease to 0 directly, meaning that the learned knowledge is reusable and is correct. So the next step is like how we can configure the prosthetic device to improve the gait symmetry, because gait asymmetry is a main factor cause like secondary issues in people post-amputation, for example, like the lower back pain. And here we introduced the anterior and the posterior ground electric force to better understand the mechanism of gait asymmetry or asymmetry. And we can see that both the stance time symmetry and step length symmetry. Stance time symmetry means how long you spent on your left and right side. And the step length is like your step length. Yeah, they both have showed significant correlation with the interlimb impulse or the intralimb impulse, and this result is consistent across all participants. And in summary, and our work has generated multiple journal articles as well as conference proceedings. And the work was highlighted by attribute spectrum as AI helps amputees walk with a robotic knee. And from now, I will shift gears to talk about neural-machine interface. So a brief background about motor control and electromyography. So here, when we move our limbs, our brain sends out control signals through the spinal cord to the motor units, a pool of motor units. Here, motor units means like a motor neuron and the muscle fibers, it innervate. And when the motor unit receives the signals from brain, it will generate motor interference. And this signal will amplified by the muscle fibers to generate electrical motor unit signal as well as mechanical force output. And when we sum all the information, we can get EMG and force output. So in summary, the EMG signal and the muscle force are well-aligned forms of the motor output. And EMG perceives force output due to the electromechanical delay. as well as like EMG will encode both the motor unit variance as well as the motor unit action potentials. Those will make the EMG a good candidate for neural machine interface for wearable robots, as well as for diagnosis of diseases. So, and now we can reverse the sequence. Say we can use the high density electrodes, measure the high density EMGs from the muscle, and then we can use the motor unit decomposition techniques to decompose the motor unit spectrum as well as the motor unit action potential. Basically, we trace back to the neural signals. This will generate more accurate motor intention estimation than the raw EMG. However, the offline decomposition method require iterative refinement, which is time-consuming and is not generalizable. But when we look at the motor unit action potentials, we can see there are common patterns, similar patterns, as you can see here. So this trigger our approach using deep convolutional neural net to estimate the neural drive directly. So here this is a structure of the deep neural net. It takes in a window of high density EMG and estimates the number of spikes in there. As you can see here, there's a pattern. Another pattern indicates 2 spikes, and here we can see a pattern is another spike. Again, we validate this with generalizability across different intensity and joint angles. We measure the EMG signals where people perform asymmetric contraction under different intensity, or like for different target, as well as at different ankle angle. We perform intra-condition validation and the inter-condition validation. Here is the example result. We can see that the diagonal figures show that intra-condition validation, and the off-diagonal show like inter-condition validation. We can see that the consistency means that the deep CNN is generalizable across those conditions. This is the same for other testing scenarios. And later on, we tested generalizability across muscles and participants. Here we measured the muscle signals from the vast lateral, vast medial, where the person performed knee extension task. We have 5 participants, 2 sessions for each participant, and 2 muscles. Here we performed the leave one out cross-validation and using 3 data sets for training and 1 for testing. We can see that the output from the convolution from the CNN is well matched with the offline blind source ambition method, indicating that this is the same for across muscle and the participants test. So basically say the method is generalizable across persons and can work in online manner. This also produced a few journal articles as well as conference presentations. And a brief summary about my future work and potential collaborations. So the 2 advanced neural machine interface and human-in-the-loop optimization will be used for neural interface development, as well as neural adaptation and motor learning mechanism study. So for the human-in-loop optimization, one study is like personalization of wearable robots with multiple joints, as well as digital twin in wearable robot personalization. This is 2 immediate research projects. So I welcome collaborations from faculties at UCF and researchers in the industry, as well as clinicians from hospitals. With that, I would like to thank the educational institutes for the diverse training I got, as well as the financial support from NIS and NIH. With that, I'm happy to take any questions. Thank you.